If you've ever wondered what makes diamonds so hard, or why graphite can conduct electricity even though it's made of carbon, you're in exactly the right place. In this video, we're going to break down giant covalent substances, what their structures actually look like, why they have the properties they do, and how to explain it properly in your exam answers. We'll cover what substances have giant covalent structures, and I'll also flag up the really common mistakes that students make in exam questions on this topic. So grab a pen, get comfy, and by the end of this video, you'll have giant covalent structures sorted. So let's start with how to spot a substance that is giant covalent. Now, there are only 5 substances that have at GCSE and A level that we describe as having a giant covalent substance. I nickname those the big 5. So those are carbon in the form of diamond, graphite, and graphene, silicon, and silicon dioxide. So in order to spot them, we learn what the big 5 are, and then we recognize them. Oh, that's carbon, it must therefore be giant covalent. Your keyword that you're going to use when you're discussing anything and everything to do with giant covalent substances is atoms. And what is the structure? It's a giant network of atoms joined by lots of strong covalent bonds. And just to break down what that means a little bit, so a giant network can also be called a lattice. So if you're more comfortable with one word or the other, then you can pick your favorite. And then also, what is a covalent bond? A reminder that it is a shared pair of electrons. So all of the big 5 have this giant network of atoms joined by strong covalent bonds. Now, that looks a little bit different depending on what we are talking about. So carbon comes in different forms. 3 of those forms are diamond, graphite, and graphene. Now, the different forms of an element, like diamond, graphite, and graphene, are called allotropes. You don't need that word necessarily for GCSE. It's maybe helpful to know for A level. So what happens in diamond is each of those atoms is making 4 covalent bonds. So that means all of carbon's outer shell electrons, because it's in group 4, are involved in those covalent bonds. Graphite, however, each carbon atom in that giant network, that giant lattice, has 3 bonds. And that means that there are actually delocalized electrons in between the layers of carbon atoms. A reminder that the word delocalized means free to move. So there is 1 electron per carbon atom that is free to move in between the layers. Graphite has lots of these layers, and there's only weak forces between them. So the layers are not actually covalently bonded together. Graphene is actually 1 layer of graphite. So it has many of the same properties as graphite because it has a similar structure, but it is only 1 layer. Let's talk about those properties in a little bit more detail, making sure that we explain what the differences are and how to explain what these properties are. So, quick reminder of some mistakes that you need to not make. So, first one is do not talk about molecules. Molecules, that word molecules, those are atoms joined by covalent bonds. You can only use that word for something that is simple molecular. Sometimes simple molecular is known as simple covalent. It depends what language is in your exam specification, but molecules are only for simple molecular, simple covalent substances. Instead, what we have here is a giant network of atoms, and that network carries on throughout the entire substance. In order to change the state, you have to break all of the many strong covalent bonds, breaking the covalent bonds. And remember, we talked about those different properties, even though they're both made of carbon. So first, let's look at melting and boiling point. So giant covalent substances, all of the big 5, there's no particular differences here. Those melting and boiling points can be described as very high. And by that, we are talking about thousands of degrees Celsius. And that's down to its structure. Remember, we have this giant network of atoms joined by many strong covalent bonds. And the bit that explains why these substances have such high melting and boiling points is because we have to put in lots and lots of energy to break those many strong covalent bonds. If we didn't have to break them, this wouldn't require as much energy. So all of the big five have very high melting and boiling points. So then let's look at conductivity, and this is where we start to get differences. Now, in general, the answer is no, they do not conduct electricity. And that's because these substances are made of atoms, and atoms are neutral. Remember, you need two things in order for a substance to conduct electricity, something that can move and something that can carry a charge. And so because atoms are neutral, we are saying there is nothing to carry a charge here. If you want a slightly more general explanation, then the one that you can give is there's no free ions or electrons to carry the charge. But if you are going to use that explanation, you need to make sure you do not miss anything out. So you can't say, for instance, there's no free electrons to carry the charge, because electrons are not the only charged particle that could be carrying charge throughout the substance. So either explanation is fine. Atoms are neutral, or there's no free ions or electrons to carry the charge, but pay attention to the wording. You can't start substituting here. You can't miss out the word atoms, substitute it for molecules. You can't say only electrons but not ions. So just get really tight, dial in on those words, and do not substitute or mess with them at all. Now that's in general. As we said, there's some pretty big exceptions here. And those exceptions are graphite and graphene. And that goes back to the structure that we talked about and the difference in the number of bonds that carbon atoms are making. So graphite and graphene do conduct electricity, which is not typical for giant covalent substances. And that's because, remember, in graphite and graphene, each carbon atom is making 3 bonds. And therefore, we have 1 electron per carbon atom that is free to move and therefore carry the charge. Be aware of a common mistake here. You can't say there is 1 electron free to move and carry the charge, because there's not. There is not 1 single electron carrying the charge throughout that entire substance. There's billions of electrons probably carrying the charge throughout the substance. So if you do want to explain it, and at A level you definitely do, referring to the bonding of the carbon atoms, then you are saying each carbon atom is making 3 bonds in graphite and graphene. Therefore, there is 1 free electron per carbon atom that can carry the charge throughout the substance. Then we have hardness. So diamond, you may or may not be aware, it's very, very hard. They use it, for instance, to tip the instruments in dentistry, because it's one of the only substances hard enough to actually do anything to the enamel on our teeth. And again, if we go back to the structure and bonding to explain this property, we have that giant network of atoms, and those atoms are held very rigidly in place by these strong covalent bonds between them. So our explanation is we have a rigid network of atoms joined by strong covalent bonds. However, graphite again is a bit of an exception. We still have a giant network of atoms joined by strong covalent bonds, but those layers of atoms can slide over each other. Remember, those layers are not actually joined together by covalent bonds. We only have weak forces between them. If you're going to use this explanation which I hope you do, in your exam questions, again, don't start missing out words here. So you can't just say the layers slide over each other. The layers of what? Cake? You're saying the layers of atoms can slide over each other. Okay, we're now going to test this out. So remember, I'm a fan of really deepening your understanding here, rather than just like rote learning some words and chucking them out there and hoping for the best. So let's drill down into that understanding. As we go through these statements, try and see if you can answer for yourself whether this is true or false. some of them are designed to catch you out. So pay attention to the wording, pause the video as needed, and then come back to my explanation. So our first one says, diamond has a high melting point because there are strong covalent bonds between its molecules. Is that true or false? It's false. It's false. And there's a couple of points here that make it false. There is one big glaring mistake there in the choice of words, and that is there are no molecules. No molecules. That should be a big flashing red light inside your brain, because the word molecules only applies to simple molecular or simple covalent substances. There's no molecules, there's a big rigid network of atoms. So we could say, right, let's just substitute the word molecules for atoms. But remember, there's another thing here as well, because it doesn't matter if we have strong covalent bonds if we didn't have to break them. So that is missing, and we need to add that in to make this statement true as well. Next one. Number 2, diamond has a high melting point because the atoms are all joined by covalent bonds in a lattice. Is that true or false? False. It's false by omission. So atoms are all joined by covalent bonds in a lattice. That bit is true, but it doesn't explain the high melting point. So in order to make this statement correct, we need to say, because the atoms are all joined by covalent bonds in a lattice and a lot of energy is needed to overcome or break those bonds. Next one. For the third statement, it says SiO2 means there is one silicon atom and 2 oxygen atoms in a molecule. Is that true or false? It's false. It's false. Again, there should be a word there that we're perhaps cottoning onto now that just makes this completely incorrect. There are no molecules. We have a giant network of atoms. So what we're saying here for silicon dioxide is, yes, we have a giant network of atoms. Those atoms are silicon atoms and oxygen atoms. The SiO2 is referring to the ratio of atoms inside the lattice. So to stitch that all together, a correct statement would look like SiO2 means for every one silicon atom, there are 2 oxygen atoms in the giant network of atoms joined by strong covalent bonds. Another way to phrase that is SiO2 means the ratio of silicon atoms to oxygen atoms is 1 to 2 in the giant lattice. Okay, let's quickly recap now. What are we taking away about giant covalent substances from this video? Only the big 5 have giant covalent structures. We learn what those 5 are, and we use that learning to recognize these substances. They are carbon in the form of diamond, graphite and graphene, silicon and silicon dioxide. We are hopefully sick of hearing this now, so we can get it inside of our brain. Giant covalent substances are a giant network of atoms joined by many strong covalent bonds. And those properties again. Giant covalent substances have a very high melting point and boiling point because we have to break those many strong covalent bonds. Generally, they cannot conduct electricity because the atoms are neutral. But graphite and graphene can, because they have delocalized electrons between the layers that can carry the charge.
Thank you for watching. If this helped you, then don't forget to hit subscribe for more new GCSE and A-level chemistry videos every single week. I look forward to seeing you in the next video.